We have now got Professor Kar Yan from the Hong Kong UST, who will explain to us in detail how AI and machine learning work, and talk about their applications in finance, such as credit scoring, robo-advising, AML. A very welcome to you, Professor Tam. I'm sure you have enjoyed the talk by Mr. Ma as much as I do. I'll leave the floor to you, and I look forward to learning a lot more about AI and machine learning from your talk.
Thank you, Casey, for the introduction. Okay, thank you. Okay. So it's a great pleasure to be here to do a little sharing, okay, on AI in finance. It's a big topic. I can spend a whole semester talking about AI and financial application. But since I only have 1.5 hours, so I try to pick topics that I believe are important. I won't go very deep into the specific technicality, but just want to give you the essence of some of the very important concepts that people talk about in recent years. So, as usual, I over-prepare. There are more than 100 slides that I have prepared for this presentation. I'm also sure we are going to go through all of them. I may jump from one concept to another, so please bear with me. So AI is a very, very hot topic these days. If you look at the search terms, the statistics of web search and news search, machine learning, big data, business analytics, AI, all these terminologies appear quite frequently. In fact, they are on the rising trend over the last 10 years. So the society is very interested in knowing more about AI and its application. So here's the agenda for today, covering a number of topics. Why AI now? What's the relationship between AI and machine learning? How do we apply machine learning models and how to evaluate them? I also want to cover a very important topic, I believe, is the difference between inferencing and prediction. Oftentimes, there's confusion between the two concepts when people apply AI in their organizations. And finally, some sample of financial applications to illustrate how machine learning and AI work. And then later on, we open up for Q&A with Nelson's support. So first question, why AI now? Now, if you look at the development of artificial intelligence over the last 17 years, you see there's some up and down. The term artificial intelligence was coined by Professor John McCarthy in 1956, if I remember correctly. So this is the first time AI was mentioned. And it actually the time where the entire discipline of AI was created. Now, if you look at the PowerPoint, you see AI has gone through at least 2 cycles. And at the bottom of the cycle, we call it AI winter. So the first hype, so to speak, is in the mid-50s and 60s. There's a lot of expectation about AI, and it's a wonderful discipline and can solve all the problems of mankind. And then after a while, people find out that it's just too much hype. The technology was not ready at that point in time. And then it came down in the 60s. And then about 15 years later, it came back again. And then it went through another AI winter. And now we are in 2021. So here's the question I pose. Will the experience that we have at this point in time is another cycle? It's just another passing hype, or this time is different? So before I give you my answer, I would like to highlight the pattern of technology adoption over time. A lot of technology actually experience this type of adoption pattern. So in the very beginning, when we have a new technology, people got very excited. and there are a lot of expectation about what this technology can do. And this, of course, including artificial intelligence. And then after a while, people think that, well, maybe the technology was not that great. It's not ready. There are a lot of technical problems that need to be solved. And then the interest died down. So it came back, and people stopped adopting the technology. And then after a period of time, when technology catch up, then the interest will emerge, and we see more and more application using the technology because the technology conditions are here. So the question is, for AI that we are currently experiencing, is it going through a first cycle? So the red arrows point out, are we in the peak of the first cycle, or are we somewhere here? So before I give you my answer, I would like to highlight that a number of enabling conditions of AI. The first is increasing number of touch points with customer. Second is unstructured data processing. Third, cheap data storage, and then high performance computing. So let's go through each one of them. Increasing number of touch points. I'm sure many of you have already experienced. When you do business or transactions with your service provider, you experience many touch points. So it could be through your cellular phone, the internet, or even going to the branch, the physical branch office to conduct a transaction. So all these touch points will leave a digital footprint. That means you leave some data behind every transaction. Now, in the past, when storage is very expensive, it's very expensive and also quite challenging to store all this footprint. But now, this footprint will stay almost forever. Just use the phone as an example. Everyone has at least one phone, and in your phone there are many sensors. And it constantly captures a lot of data. For example, the location through the GPS, your physical movement, the call log, the application log, browsing history. A lot of information is collected by just a single device. And I'm sure you have many other devices in your pocket. Well, you may have Apple Watch, a whole bunch of credit cards and payment cards. And you also use social media on a daily basis. All of this collectively are the touch points. And through these touch points, you leave your own digital footprint. And with the emergence of Internet of Things, there are more and more devices, sensors all around you. And all of this, again, further push the envelope in terms of collecting data from the individuals as well as from an organization. So this is the first condition, a lot of data. Now the second enabling condition is we are able to process unstructured data. So what is unstructured data as compared with structured data? Structured data has a structure like a table. Excel is a good example of structured data. Relational database is another example. So the data about a person, about a company, about a phenomena are expressed in a table form, and we call them structured data. Now what are unstructured data? Data has no fixed format. For example, an audio file, a video, your Twitter text, a video on the YouTube. So this data cannot be easily expressed in a table form. In the past, it's very difficult to process unstructured data, but now we are able to do so. In fact, the explosion of data in the past 10 years or so, most of them is because of the explosion of unstructured data. As you can see from the graph down below. So the orange bar corresponding to the volume of unstructured data, and the blue bars corresponding to the traditional structured data. So there's an exponential growth of the unstructured data collected through all these touch points. I'll give you one example. So this is an image from a satellite. Now, in the past, if you want to get a satellite image, it is very, very expensive. Now you can get a satellite image almost free. Now, with this high-resolution satellite data, there are a lot of information embedded in it. So in this slide, you see two images. This is an image about a certain part of a city. Now, people come up with a very clever way to extract information from the image. So to monitor the economic development of a city or a particular region, you can look at the satellite image and extract how fast construction proceeds. So how do you know whether a particular region has a lot of construction or not? Well, you look at the shadow of the buildings. If those shadows increase and over time, then you can draw a conclusion. Maybe more buildings are put up in that particular region. And in the past, this can only be done by the security or military agency. But now, ordinary people, ordinary organizations, you can download a copy of the satellite image. As long as you have the creativity, you can create value from analyzing all these satellite images. So my colleagues in the finance department at HKUST Business School, they conduct a research, basically employing the idea I just mentioned. So they get hold of satellite data, and they want to track some macroeconomic data. In this case, the inventory of oil in the United States. So what they did is they get satellite image of the oil storage hub in the state, and then look at the shadow of the oil tank. Now, if there's a lot of inventory, the oil tank, the height of which will increase, and that casts a shadow, a different shadow on the ground. And by estimating the area of the shadow, they come up with a proxy of the inventory level of the oil, oil storage in the United States. So the whole point here is to point out that we don't need to rely on the government on macroeconomic data. In fact, with satellite images and other technology, we can actually get most updated information about this data and don't need to rely on the government. And there are a lot of policy implications as a result of this. The third condition is cheap storage and connectivity. So this graph shows the cost of 1 gigabyte of data. So if you look at the left-hand side, well, I can't see it here. I think it's 1980 or so. It costs about $1 million US for 1 gigabyte of data. And if you move to the right-hand side, it's getting cheaper and cheaper. It's less than 10 cents now. Probably much so. So the cost of storage is exponentially declining. It almost costs nothing to store something forever. So that was advice actually I told my students in my class actually starting many years ago. If there's anything that you will regret 5 years, 10 years later, never put it up on social media. okay, it will stay there forever. Okay, you cannot delete it. Okay, so. Now, another development is storage. A lot of time, personal data as well as organizational data, they don't store in your own computers or server. Okay? More and more, you store in the cloud. And these clouds are operated by a few operators worldwide. The famous one, Amazon, Microsoft, Alibaba. So increasingly, the storage is outsourced to these cloud operators. Okay? And of course, you pay less, and that's the economy of scale. But on the other hand, you have to rely just on a very, very few providers worldwide. Okay? And that's a risk because the industry is so concentrated. Okay, so the four conditions: cheap and high performance computation. So this graph shows the calculations per $1,000 over time. The y-axis is an exponential scale, and as you can see, over time, the power of computers has grown exponentially. And there's a very famous law, many of you may aware of that, is the Moore's law on computation. Basically, it says computing power will double every 18 to 24 months. And it has been happening for the last 6 decades. So if this is anything of indication about the trend, and if you believe in Moore's law, there will be continued growth in terms of computation power at the exponential level. There's a lot of research going on in quantum computing. This is another new development that the finance industry should pay attention to. So the performance of computer is coming to a point that it starts to challenge the cognitive ability of human. Many repetitive tasks, a computer is better than many humans. But in something that requires a lot of deep thinking and intelligence, such as the Go game. Now, computer AlphaGo has beaten the world champion. And AlphaGo's algorithm is a mix of different machine learning and search algorithms. So these are the 4 enable conditions of AI. AI went through 2 AI winters, so to speak, because these conditions were not there. So I believe that we are now at the point of the blue arrow. The 4 enabling conditions are here, and AI will going to make a significant impact on every aspect of a society. So that leads me to the second topic of today, AI and machine learning. Now, actually, I have done work in AI many years ago. In fact, my PhD thesis was in pattern recognition in finance. So I had a chance to actually witness the up and down of the AI winter, at least the second one. So I want to compare 2 approaches to AI. One in the 1980s and one that we are experiencing right now. I want to clarify that AI is not machine learning. Just about 30 years ago, another rise of AI. People use deductive reasoning. So there are 2 types of reasoning: deductive reasoning and inductive reasoning. Right now, most of the research and applications are based on inductive reasoning. I will show you a little example, okay, what's the difference between deductive reasoning and inductive reasoning. Okay? But I just want to make a point that deductive reasoning is also very important. But at this point, most of the attention is not devoted to this subject. Okay? So in preparing for this presentation, I went back to my old research work and tried to dig up something. Okay? I find one paper that I published more than 30 years ago. The title is Adapting Expert System Technology to Financial Management. Now, expert system technology is one of the deductive reasoning technology, and the firms actually use in developing financial applications. If you look at the table in the middle, expert systems for financial application, you see some names. Some of them are still around. For example, AE and SEC, but some has gone, or merged. For example, Coopers and Lybrand, Alfred Anderson, Bank of America is still here. And if you look at the application area of expert system, more than 30 years ago, it has a lot of resemblance to what we are building right now. You see trader assistant, you see portfolio advisors, you see credit scoring. So the finance industry actually has been adopting technology for many years. And what we are doing right now using machine learning is very similar in terms of the objectives 30 years ago. So what is an expert system? And what's the difference from machine learning that we have right now? Now, the name expert systems mean we want to code the human expertise into a knowledge base. And then we apply some inferencing mechanism to answer questions from user. And the focus of deductive reasoning is on knowledge representation. How do I represent the expertise, the knowledge, the wisdom of a human expert in some symbolic form? A very common way to express this knowledge is the rule set, which is shown on the right-hand side of the slide. So basically, a set of rules for a particular domain, and these rules are derived from human expert. So in this case, this is a rule set for dividend policy. So if a manager would like to seek some advice on the dividend policy, the person will log into this expert system and to answer questions posed by the expert system based on this set of rules. So this is how AIs function 30 years ago in the form of expert system. And there are many of these expert systems, as shown up here. So it hit the wall, this approach. Why? First of all, knowledge acquisition and transfer is very difficult. And there's also, there's no incentive for the human experts to transfer his or her knowledge to a computer, because they all afraid that the computers will replace them. Second is the benchmark of any expert system. The best that you can get is the human expertise. So the question is, can an expert system outperform human? Unlikely. And also, many knowledge cannot be expressed in rule format. So after a few years of popularity in the late 80s and early 90s, the expert systems died down. And that enters into the second AI winter. So the rise of AI or machine learning right now start around in 2006. So AI is not machine learning. Machine learning is just part of it, okay? And also the term deep learning, okay, is also, okay, part of machine learning, okay? It is not the whole thing AI, okay? AI consists of many other things. So I would zoom in, okay, given the time I have, okay, I will zoom in, okay, to machine learning, okay, and we'll focus on supervised machine learning, okay. So let me go to this page. Now, when we talk about machine learning, there are basically, okay, three major categories of machine learning. One is supervised learning. The other is unsupervised learning, and then we have reinforcement learning. And these are the different branches of the machine learning discipline. For this talk, I will focus mainly on supervised learning, okay, and get into a little bit deep, okay, especially in classification. So, okay, the idea of supervised learning, okay, is like this, okay. You want to make a decision, yes or no. Okay? You want to do a classification. Is this an apple or is it an orange? Okay? This is the output. Okay? And you want to explain this output using some other piece of information. And we call it, okay, the input factors. So what supervised learning does is, okay, you provide a lot of examples, okay, of apples and oranges. Okay? And you also, okay, provide an algorithm. The algorithm will try to learn, okay, from all these, okay, examples of apple and oranges, and try to come up with a rule, a decision rule or a function, okay, to classify future, okay, objects into apple and oranges. Okay. So the name supervised learning, okay, supervised means, okay, you use the labels, okay. You use the examples, okay, to help, okay, the algorithm to learn. Okay? So many applications, okay, in the finance, in Fintech, okay, are solution based on supervised learning. Okay. Now, unsupervised learning, you don't, okay, have labeled data. You do have data, but you don't have, okay, labeled data. So the whole idea of unsupervised learning is to find patterns. For example, here, okay, there are two graphs. The graph on the left-hand side, you see a large number of dots. Okay? But you probably can see there are at least, okay, two clusters of points, right? So unsupervised learning tries to help you to find all these patterns. Okay? So the image on the right-hand side shows that unsupervised learning algorithm actually, okay, identify three clusters represented by the green, the blue, and the red. Okay? Unsupervised learning also, okay, has been used, okay, to do dimensional reduction. Okay? So this is a very important, okay, task. Okay? If you have a lot of dimension, okay, a lot of data, and each data point described by many, many different dimensions, it is very difficult to handle. So if you can reduce, okay, the dimension, okay, from a large number to a small number, it really helps, okay, in terms of the performance of the algorithm. Now, reinforcement learning, okay, I won't go, okay, I won't talk too much about reinforcement learning. Basically, okay, it is used to work out a plan. Okay? So the reinforcement learning, okay, the output of which, okay, is a plan of actions. Okay? It has no label examples. Many solutions, okay, involving, okay, learning how to play a game, okay, will use reinforcement learning. Okay. Again, okay, for this talk, okay, I will focus, okay, mainly on supervised learning, okay, and in particular neural network. Okay, people talk about, okay, a neural network, okay, quite often this time. Okay. So the notion of neural network, okay, of course, has this biological, okay, origin. Okay. The the image on the left-hand side of the slide is a picture of a biological neuron, and the neurons are connected by this connection, and they send signal between each other. And the image on the right-hand side is an artificial neuron. So it actually accepts inputs from other neurons. As you can see, the W1, W2, W3, W4. These are the weights of the connection. So the inputs are from other neurons, and the inputs are weighted by the weight shown on the connection. And there's a function to combine all the weighted input and send an output. So in a nutshell, a neuron, which is a basic building block of any neural network, looks like this. A very complex neural network simply means it has a lot of these neurons, a lot of neurons, a lot of connections. Okay, coming back to this extra growth development. So the machine learning come back in around 2006. Why? Because the conditions I just mentioned, the four conditions, start to appear. It become mature. Computers become faster, and there are more and more data available. So the neuron evolution. So the perceptron on the left-hand side, which is a single neuron, it was developed in the 60s. It only performed very few functions. In the 80s, when neural network start to see some simple application, it has one layer. And now we are talking about deep learning neural networks. We are talking about hundreds of millions of neurons. There are many more things that we can do with multiple layer neural networks than compared with the perceptron in the 60s and the single layer neural network in the 80s. Well, since I dug up my previous work during Easter holiday to prepare for this presentation, I find one which I've done again almost 30 years ago. Basically, to apply a neural network to predict bank bankruptcy. The research was motivated by the saving and loan crisis in 1987. And I was, at that point in time, I was a faculty member at the University of Texas at Austin. And the state had a lot of bankrupt banks. So I have a lot of data. But the challenge is I have to code all this data manually in a data file, and I have to write all these algorithms myself. So just to give you a taste of what the neural network looks like 30 years ago and apply in financial context. So the input layers consist of the regulators information. For example, capital asset ratio, all this data that you have to report to the regulator in Texas at that point in time. And the output, there's only one output up there of the neural network, is a score from 0 to 1. So it measures the likelihood of bank failure. So this network can be used at that point in time as an early warning system. So the banks file their quarterly report, and the information, the data in the quarterly reports back to this neural network, and then come up with a score. And then the auditor will depends on the value of the score. If this is highly likely to fail, then of course the physical site audit is needed. If not, then maybe the energy should focus on other banks. So this is the early applications of a neural network in a financial context. Then why a deep neural network? Why deep means there are more layers. So instead of a single layer in between the input and the output, we have many layers in between. So that is the depth of the network. If you have a very deep network, meaning that you have a very large number of hidden layers. Okay. Now, why we need to add more layers to it? Okay. Well, more layers meaning that more neurons and more weight. It turns out that if we have more and more data, and if we apply the same old learning algorithms, for example, a neural network with just one layer, the performance cannot be improved substantially. But if we add layers of neurons in between, it can scale up correspondingly. It gives you maybe two very simple examples. So one is the handwritten digit recognition, and the other is facial recognition. So the problem is very easy to understand. How can you train a machine to recognize handwritten digits, and also the face of a particular person? So very easy to explain to anyone this problem. But it turns out to be very, very difficult to solve. Even if you have a neural network, if it's just one layer, it's very difficult to solve. Okay. So then we have to rely on deep learning. We add more hidden layers, and it will help to improve the performance. Now, why it works? Okay. It turns out that with more hidden layers in between, the input can be transformed into different space. And by doing so, the neural network can actually retrieve some of the important features of that object. We don't need to tell the neural network what are the important features. But somehow, with enough hidden layers, the network somehow can pick it up. One example in visual recognition is the shape of the face. So if you have one hidden layer, it's very difficult to capture this curvature and also the boundary between the face and the background. So it all sounds very complicated, right? I mean, we have hundreds of millions of neurons and also many ways connecting them. But it boils down to a few components for supervised learning. First of all, is the output. What is the decision that you're making? And then the input, what are the input factors or data that you need to make that decision? So you can express this as a very simple function, a function that map x to y, and you need the data, you need labeled data. The data will help you to find a function that come very close to the one that you probably don't know. So I'll give you maybe two examples to illustrate this. So here we have a function. So we want to recognize the digits 0, 1, 2, 3 up to 9. And here we have to define two things. First of all, how do you represent a digit? So down below we have three options. One, we can represent a digit using a matrix, 8 by 8 matrix. The middle one is 32 by 32, and then we have a more high resolution matrix 28 and 28. So from going to 64 to 32 times 32, we actually increase the accuracy of the representation. But the trade-off is we have a lot of inputs to deal with. So at the far left, with only 8 by 8, we have 64 input, which is much less than the one on the far right, 128 by 128. So this is one. The other is we need to have all the handwritten digits to interlay on all this matrix. Okay. And with that, we can start to learn how to differentiate between a digit 0 from 1, 2, 3, and vice versa. Okay. So the idea is very simple. You give me a lot of, say, for example, you want to recognize the digit 2. So you give me a large number of handwritten digits examples, which is 2. And then you give me a lot of non-2 examples. We call the negative examples. So given the positive examples and also the negative examples, you fit into a machine learning algorithm. It could be a neural network. It could be a logistic regression. It could be other techniques. So the whole idea is you build a function. That function will classify any handwritten digit and recognize that whether this is a 2 or not. So that's simple. So there are some basic principles of machine learning applications. Machine learning application works under these 3 principles. First of all, the images, the text, the decision, the behaviors that we want to classify or predict, they are not random. If things are really random, it means there's no pattern. If there's no pattern, there's nothing to learn. So the first principle is things are not random. The second is, if there are patterns, if there are relationships, then they can be analyzed or identified by looking at enough number of examples. For example, to differentiate between apple and oranges. Under this principle, you ask for a lot of examples of oranges, a lot of examples of apples. And then you fit it into a learning algorithm, and hopefully, with enough example, the algorithm will come up with a decision rule, a decision function to differentiate between apple and oranges. And all this decision-making process will be helpful to the individual and organization. And you see many of these contexts in Fintech. Here's another example. So instead of recognizing digit, now you want to make a decision whether to approve a loan application or not. So the X are no longer a pixel in the matrix in the handwritten digit recognition problem. The X here could be age, could be gender, annual salary. So in this example, I use 7 inputs. And the third column shown in red is a particular example in this 7 dimension. So to build a loan approval system using machine learning, you will have 2 samples of data. One are those applications that turn out to be okay, meaning that the person who got the loan, he or she pay off all the loan. So a very good customer. So this is a positive example. And then you need to collect another set of examples. Those are the loans that are defaulted. So bad applicant. And you want to see if there are any similarity between the good applicants and also between the bad applicants, and find a way to differentiate them. So you have these 2 set of examples, and then you fit it into, say, a neural network. And then the neural network, after a number of iterations, will come up with a function. And that function is represented by the weight of the neural network. So here is the function, approve or reject. So even though the application's contexts are very different, one is digital, handwritten digit recognition, the other is loan approval, but the principles are the same. The components are the same. So I mentioned about neural network, which is shown below, but there are different ways to represent a function. It could be a simple straight line regression shown on the upper right-hand corner, or it could be an S-shaped logistic regression, It could be a decision tree shown on the lower left-hand corner, or it could be a support vector machine. So there are many, many different ways to represent a function. For a neural network, again, these are the collection of weight, and the number of neurons. So collectively, this represents a function. So there are many, many techniques and algorithms that you can find. Many comes with open source software, so you don't have to program. These are all the source code that you can actually download. So now it's very easy to run machine learning algorithms. So, let me summarize the typical steps to apply machine learning. So the first is to formulate the right questions. Interestingly, in many projects that I work with the industry, this actually spend a lot of time, it turns out. How to formulate the problem in the right way is very important. And then you develop the model, and then you automate your decision making and redesign the business process. So step one, identifying and framing the questions. So here's some examples in the finance world. Is this wire transfer suspicious? So the answer is yes or no. As you can see from this list of questions, a lot of time, you can frame this as a classification problem. You have inputs coming in, and you want to classify the outcome into one or many of options. So, for example, take the first one: is this wire transfer suspicious? So there's a wire transfer transaction initiated by a customer of a bank. So the bank needs to check right away whether this wire transfer is suspicious. So it's a real-time decision has to make. The bank cannot afford to ask someone, to a human being, to actually look at it. So a machine learning application in this is to come up with a decision model. Based on a number of factors, for example, the transaction amount, the transaction history of the person, and also the recipient side. So all these factors are the X, and the Y is a very simple classification, yes or no. Similar for the other questions up here. So, and then develop the model. Once you have the Y defined and the X, then you develop the model. The model could be a neural network model, a deep learning model. It could be a decision tree. So once you identify the model, you pick one of these algorithms to implement it. So let me skip this. So this is an overview of the different steps. For supervised machine learning, first of all, you identify the question. You have to frame the right question, and then based on this question, you find the appropriate X and Y, the input and the output. And then you try to find collection of examples of the input and the output, and then you build the model. Now, but once you build a model, you won't stop here because you want to know, how good is this model? Say you have a loan approval system developed based on a neural network. How good is it? So there's an extra step of cross-validation. And that it comes to another topic on overfitting and evaluation of a machine learning model. Now, I mentioned that you build a model using a lot of data, examples, labeled data. Now, if you use the data that you build the model to test the model, the result will be very biased. Okay. Because there's a possibility of overfitting. Okay. So let me show you graphically what that means. Okay. So we have a number of red dots, expressed in x and y. A very simple function. We have only one x and one y. So we want to find a function that actually fit these data points. So if you look at the graph on the left-hand side, so the model is a very simple regression model, a straight line, a linear regression model. Somehow it captures certain pattern. There's some kind of positive correlation between x and y, and this linear line capture it. And you look at the one on the far right. So a lot of curvatures. So it's not a straight line. It's a very complex line. Up and down, up and down. So it actually captured the data points better than the straight line. And the graph in the middle is a graph just capture the curvature. Now it may not be as good as the one on the right. It's better than the one on the left. So it illustrates two things as shown below. The complexity of the model. So complexity increase from the straight line to a high polynomial function on the right-hand side. It also creates a higher chance of overfitting. Overfitting is no good because especially when you use the model for prediction. So somehow we have to make a trade-off. Here is another example. So this one involving classification. So again, we have a two-class classification problem here, the X, the cross, and also the dot here. The cross in red and the dot in blue. So we want to find a function to separate the X and the cross and the dots. So the one on the left-hand side is a very simple linear classification. Basically, it's a line that draw in the middle. It has some error. For example, on the right-hand side of that line, we see some cross. On the left-hand side of the line, we see some dots. So these are the errors. So in terms of accuracy, it's not very good. Now, if you look at the far right-hand side, we have a very, very complex boundary to separate the dots and the cross. Almost perfect classification, no error. But the boundary is very complicated, very complex. So a question arises, if which one give me a better prediction if I have a new objects coming in? It's likely it's the middle one. So the middle one is a compromise between a very complex model, very specific, but not general enough, with a very simple model, but very too general. So here's the concept. So even though you don't know the mechanism of neural network and all this fancy terminology, but when someone show you a machine learning model to solve some problem, you should ask this question. First question is, what's the performance of the model using the training data? Oh, 99.9%. Well, great. As expected. And then you should ask another question. What is the performance of the model based on the validation data? The two are not the same. So if you have a good performance on the validation data, okay, you feel more safe. Okay. So how do you get the validation? Okay. Very simple idea, okay? The concept of whole-out data validation. Okay. Okay. Let me give you an example. Okay. If you recall, okay, you need training examples to build your model. Okay? For classification, you need the positive and the negative example. Okay? Now, you want to divide this example into two parts. Okay? One is called a training set. This is the training set that you build the model. And then you reserve a certain portion, okay, maybe like 20%, 30%, okay, of the data, okay, and then call it a test set. You don't use the test set to build a model. You only use the training set to build the 70% to build the model. Once you have the model, you use the test set, okay, to test the model. Okay? And the performance of the model is based on the test set, not the training set. Okay? So typically, okay, people will use like 20% or 30%, okay, for the test set. Okay? So this is a very simple idea called a simple whole-out validation exercise. Typically, okay, people, okay, will do more than that. They will adopt, okay, something called, okay, a K-fold validation. K typically is 10, 10-fold validation. Okay? So let me show you how it works. In this case, okay, I show you a 4-fold validation. So for a 4-fold validation, you divide, okay, the original data set into 4 parts. You use 3/4 to train the model. Okay? You have 1 model. Okay? And then you use the remaining quarter to test the model. Okay, so this is, okay, one round of exercise. Okay? And then you repeat it, okay, for the other, okay, quarters. Okay? So for example, in the second, okay, exercise, you take out a different quarter, okay, and then you have another 70% for training, okay, and then another, okay, quarter, okay, for testing. So as a result, okay, you do 4 exercises. And every time, okay, you, okay, take out a different quarter of the data set. Okay. So that means you will have 4 validation results. And given this 4-fold validation, you take the average, okay, of the testing result, you divide by 4, you add them up, divide by 4, and this is the performance of the model. Okay. And typically, a 10-fold validation is very common, okay, in machine learning application these days. Okay? So you take 10% out, use the remaining 90%, okay, to build the model, okay, and then the 10% to test it. And then you take another 10% out for another exercise. You repeat it for 10 exercises, and then take the average. Okay? So, okay. Now, once we have the accuracy, okay, of the model, okay, you can build, okay, a matrix like this. Okay? Well, the technical name for this matrix is confusion matrix. Okay? Well, maybe it's you intend to confuse people. Okay? But it's just very common sense. Okay? We need to have 4 accuracy measures. Okay? We want to know, okay, the percentage of true positive, okay, corresponding, okay, to the upper left-hand corner, and also the true negative, okay, corresponding to the lower right-hand corner. And then the false alarm, false positive and false negative. Okay? And this will be the output, okay, of a machine learning application system, okay, for classification. Okay? You want to get a sense, okay, in terms of accuracy, okay, and also, okay, in terms of the false alarm. Okay? So you may want to set some threshold. Okay? Well, I cannot afford a false alarm of certain percentage. Okay? If the model, okay, cannot succeed in giving you that threshold, okay, you may need to go back, okay, and, okay, maybe build another model. Okay? So. So let me move on to another topic called inferencing and versus prediction. There's a lot of confusion between these two concepts. And I just want to maybe spend a few minutes to explain this with the use of an example. So machine learning models serve two main purposes, prediction and also inferencing. Now, you ask different questions under these two categories. Now, for prediction, you want to know, well, for example, is this a suspicious transaction? Will the stock price move up tomorrow? So you want to predict an event in the future, or you want to classify objects that you have never seen before. So this all belongs to prediction. Now, in inferencing, you want to understand the relationship between, say, objects, between phenomena. For example, can read investment hedge against inflation risk? So here you're actually talking about, is there a relationship between read investment and also inflation? The second question here, for example, which promotional campaign lead to most customer conversion? So in inferencing, you want to understand. In prediction, your concern is accuracy. So as long as I have high accuracy, I may really need to know exactly what's going on. So you heard about black box operation of the neural network. Why black box? Because the neural network is very good in terms of prediction. You have a lot of input, and you have hundreds of hidden layers in the neural network, very deep, and then you have the output. So fitting the input, you get output. So as long as the output has a high accuracy, then you are satisfied, because you are concerning about prediction only. But in many applications, you also need to understand why you have this output based on this input. And if this is your question, this is understanding, and that falls into inference. So, pardon me by showing all this equation, but I just want to make a point that for inferencing, you develop a model, you still need the data, but you tend to use simple model, and you try to interpret the output of the model. That interpretation will help you to answer the question that you pose. So let me use an example to illustrate this. So quite a number of years ago, I worked with a restaurant brand in Hong Kong. They want to predict as well as explaining the daily sales of the restaurant. So the why, well, is one. I cannot disclose the name of the restaurant. I sign all this NDA. But it's one of this brand. So, what is the why? In this case, the why is the daily sales of the restaurant chain. And what are the factors? So, here are some of the factors. I just pick a few for illustration purpose in this talk. And I also collect 2 years of daily sales data from the POS of the restaurant chain. So I know exactly the items ordered in every transaction, the time, and the location of the restaurant. So first step in applying machine learning is what's the Y and what's the X. Okay, now it's clear. Y is daily sales. The X are that could explain or predict daily sales. Okay, are the sales of the previous day. Whether that day is a weekend or whether it's a weekday, whether that day is holiday, the temperature of that day, the ring level, and also promotion. So these are very common factors that a lot of people can come up with. Okay? Of course, we do not need to limit by that. But again, for this illustration, I just make it simpler. Okay, so this is the weekly sales over time. 2 years of data. Okay. So you see 2 peaks, actually 4 peaks. Some of you already probably can identify that these are the sales in Christmas and also Chinese New Year. Okay. Well, just a suggestion. Okay? So when you deal with data, big data or machine learning application, if you have data, the first things that you may want to do is just plot them, just get a sense of how the data looks like. Okay. So this is weekly sales data over a period of 2 years. And this is the daily sales. You see a lot of spikes. Okay. So without even running any analysis, you can hypothesize that, well, these spikes are likely caused by the weekend effect. So even without running any model, you can see, well, maybe weekdays and weekend have an effect already. Okay, how to measure temperature and rainfall? Well, should we use the average temperature and the average rainfall reported by the Hong Kong Observatory to run the data? Probably not. Why? Because the restaurant chain has many outlets. There may be an outlet in Central, and another outlet in Mong Kok. But Mong Kok is raining, but Central is not. So what we have done, we actually collect the temperature and rainfall data, at the sensor location of the Hong Kong Observatory. So we find the sensor that is closest to a particular outlet of the restaurant, and we use that data for that particular restaurant. So what show up here are the different sensing devices location of the Hong Kong Observatory. So the point I want to raise is, well, this may not look like fintech at all, but I want to raise that you have to be creative in identifying data. And this is very important. So for us, if we just use the average daily temperature or daily rainfall data, basically is not useful. So that's why we drill down to the level maybe at the street level. Okay. So this is again I brought it out. This is the average temperature daily, and also the rainfall. As expected. In the middle, probably summertime, you have more rainfall, and the temperature is higher in the summer. Okay, how to measure printed ad? So it turns out that the firm has no record of any purchase of promotion with the media. So zero information from the firm. So we have to come up with a way to measure printed ad. And luckily, we come across a data vendor called Visor. So Visor has archive of all the printed media in Hong Kong. So working with Visor, we can actually identify the printed ad coverage of the restaurant. So this table shows that if the restaurant has an ad put on, say, the newspaper or the magazine, we have a record here. So which newspaper, which magazine, what day, which section of the newspaper, the circulation of the newspaper, and also the value add, the ad value of this particular media ad. So we have collected then all the data we need to run the analysis. Just want to share an experience with you that collecting the data, cleansing the data, likely require more than 80% of the time of a project. So don't underestimate the effort that you need to put in. Running the analysis could be relatively straightforward, but collecting the data so that it can be used for analysis typically requires a lot of effort. Okay, now we have all the data. And then we can fit the model. So we have 4 models. For illustration purposes, I just pick 4 different regression models. The first one is very simple. So it say today's sales is based on yesterday's sales. Model 2 is more complicated. It takes into account of the weekdays and holidays effect. Model 3 takes in the temperature and the rainfall, and model 4, advertising, the printed media effect. So we have 4 models with increasing complexity. So here are the results. So for those who still remember how to interpret the regression model, you probably can right away understand which factors is important. Now, coming back to the inference and prediction. Now, if you are interested in understanding whether any of these factors have a relationship with the daily sales, this table will give you the answer. If you look at model 1, it says, well, today's sales depends on yesterday's sales. Somehow yesterday's sales capture some kind of momentum. Is it true? Yes, it's true. It has an effect. So the asterisk right next to the coefficient of the model, for example, on model 1, 0.5. So this is the coefficient of the sales factor, and it is significant statistically. So it's important. But does model 1 explain daily sales very well? No. If you look at the adjusted R-square downstairs, it's 0.25, which is very distant from 1. Okay, so let's move on to model 2. Model 2, we include the weekdays and also the holidays effect. So as you can see, model 2 is a big improvement over model 1. By just looking at the adjusted R-square, it goes from 0.25 to 0.72, a big jump. Why is big jump? Because the weekdays and the holiday effect explain a lot of the daily sales. You can even drill down into which day has the highest sales and which has the least. So the least is Monday. Is minus 23.66, and it's significant. And the Saturday turns out to be the day that generates the highest sales on average. So moving on to model 3, the difference between model 2 and model 3 is model 3 add temperature and rainfall, and the data is collected from the Hong Kong Observatory. Now, the question is, does this factor, temperature and rainfall, will they help in explaining sales? If you look at the asterisk and also the coefficient, yes, but very, very, very marginal. And it's also reflected in the adjusted R-square. It grows from 0.72 to 0.728, which is a very small increment. So the conclusion is, Well, temperature and rainfall only have minimal impact on daily cells. Okay. So we move on to the most complex model, Model 4. Okay. In Model 4, same as Model 3, except that we add another factor, advertising. Okay. Now, if you look at the coefficient of advertising, it is very, very small, almost close to 0. And if you look at the adjusted R square, it's no difference from Model 3. So the conclusion here is advertising based on printed media as it was so executed has no impact on daily cells. Now, when I present this to senior management of the firm, of course, the marketing director jump up and try to find a lot of reasons to defend this. I mean, as expected. So the person actually suggests, oh, maybe there's also like a lag effect, which is certainly something that we should take into account. For example, you put up an ad in a newspaper, there may be a lag effect, maybe a lag 1, a lag 2 day effect. So we actually went back and test all of this, and it turns out, again, to be insignificant. So even though this project, the original idea, was not to look at the relationship between advertising and also daily cells, but the byproduct of the analysis turns out that, well, we get better understanding about the impact of advertising. And then it catch the attention of the firm. So this is actually turned out to be a very important findings, because it is a triggering point for the firm to review the advertising strategy. Now, we cannot conclude that advertising is not important. What we can conclude is that the way printed ad is being executed at that point in time, it was not effective. So this is an example that if you frame this as an inferencing question, this is how we answer the questions. Now, if we frame this as prediction, then what we care is whether by applying this model we can actually make accurate prediction of daily cells using the same set of factors. So let me show you the prediction results. So as I mentioned before, if you use the same training data for testing, it will be very biased. So what we have done is we use the first year of data to build the model, the same 4 models. And then we apply the 4 models to a new set of data, which is year 2. So we separate the training data from the testing data. And here's the result. So the gray line here, these are the actual cells in year 2. And the black lines corresponding to our prediction, the prediction given by the model. So as you can see here, the prediction given by model 1, which is the most simple model among the 4, is not very good, because it fails to capture the peaks. Now this is model 2. Model 2 include both the weekdays and also the holiday factors. So it's a big improvement over the model 1 in terms of prediction. So moving on, model 3. This is model 3. If you compare model 3 with model 2, you see some marginal improvement. So model 3 incorporate the temperature as well as the rainfall data. Now, if you compare model 4 to model 3, you basically cannot observe any. I'm actually switching between the different models. So model 3, model 4, model 3 here. Basically, it's statics. There's no difference. So this example is very interesting because it illustrates that prediction and the conclusion that we draw from inferencing, they are all aligned. Okay? So model 2 will give the base incremental contribution. So the major factors are whether it's weekdays or whether this is holiday. Okay? So now the model that we use here, let me go back. It's very simple. This is a linear regression model. Now, if you want to be more complicated, so instead of using a regression line, we use a neural network. Then the input will be, again, sales, weekday, holidays. There may be some 1 or 2 or 3 multiple middle layers, and then the output. So that as a whole is a model. And then basically, if you use a neural network, you cannot do this. And that's why neural network is sometimes being criticized that it's just a black box. It may be useful for prediction, but there's no way for you to understand how all these ways work, and how do it capture the different relationship. So, so let me move that. So some takeaway in terms of the basic principles of inferencing versus prediction. Now, if your focus is inferencing, if your objective is trying to understand the relationship between different factors, I would suggest that you use a more restrictive model. Restrictive model means it's a simpler model. For example, a linear regression. Don't go on to use a neural network because it won't give you much information. Now, a very complex model, it may fit the data better. It may give you good prediction, but quite often, it's very difficult to interpret. So it's task dependent. So if the task require you to only have good accuracy, for example, facial recognition, recognizing handwritten digits. So you don't really care, whether a particular pixel, or particular facial features, will add to the accuracy. All you care is about the overall accuracy of the prediction. In this case, explanation, inferencing may not be very important. But on the other hand, if you really want to get some insight, then inferencing is something that maybe you should consider rather than prediction. Okay, so maybe I skip some of this. Okay, so let me give some example of financial applications. Well, turn out that it's likely that I can finish all my 100 slides in 1.5 hours. Okay, one application that I think is quite common now is credit scoring. So the traditional way to do credit scoring is based on historical data. In fact, the vendors actually can sell you a credit scoring model. It's either based on a simple linear model or S-curve logistic regression model, and sometimes it's a tree-based model. But the data actually come from the database of the banks and the financial institution. Now, more and more, the credit scoring system can move beyond the boundary of a bank or a financial institution. It moves on to, for example, social media. It moves on to look to the footprint of the applicants left in the social media. And you have more and more data. Many of them unstructured data. So you need a powerful model to incorporate them. and then machine learning becomes very useful. So these are some of the data that currently being used to make a credit scoring decision. Of course, each country, each jurisdiction has its own data privacy regulation and procedures. In some countries, where you have a very tight data privacy legislation and compliance requirement, you may not be able to get a lot of data from the other footprints. But in some countries, it's more open and flexible, then you got more data. So on the right-hand side, it's a very traditional credit scoring model. It's a logistic regression. Basically, you have a lot of input, and then you fit it into a logistic function. And the output of the function is between 0 and 1. You can interpret like 0 is very high risk, 1 is not. And then you have a cutoff somewhere between 0 and 1, and that will be your decision. Now, using a machine learning approach, for example, a neural network approach, all this input is fit to layers of neurons. And the model becomes very complex than a logistic regression. Now, even for a logistic regression, you can answer some question from an inferencing perspective. But if you move to a neural network, basically it's very difficult to explain the outcome. So, and sometimes for regulatory consideration, you need to explain maybe to the regulator why a particular decision is made. So using logistic regression or decision tree, you can trace back the reasoning. But if you use a neural network, it's very difficult. Robo-advising in wealth management. So wealth management, I think for many years, is a growing industry. There's a need as people accumulate wealth all over the world. They need professional services to manage their wealth. So in the past, wealth management is done by human wealth manager, private bankers, and you have to have a minimum balance to get the service, and also the service fee is also very high. And that's a trend that this advice will be offered not by human but by system called robot advisors. It's very popular in the US and China is catching up, and I think Hong Kong is catching up as well. If you watch the TV recently in Hong Kong, you see more and more financial institutions, including banks and even insurance company, they start to promote their wealth management services with the support of IT. Likely, the IT application is a robo-advisor. So these are the typical input required for investor to get some recommendation on their investment portfolio and how to manage their wealth. Well, the first factor is the risk preference. And typically, this risk preference is captured by asking the customer to fill in a risk survey. Consists of a number of questions asking about investment experience and also exposure to risk, their tolerance, what kind of product that they have purchased in the past 5 years or so. So that is the risk preference part. The second part, we'll ask, what is your return expectation? What do you expect in 5 years' time, in 10 years' time? What is the annual return from the investment? And then the third is the investment horizon. Is it 1, 3, 5, or 10 years? So based on these 3 factors, a recommendation will be made to the investor. Okay. And also, the investment will be based on a pool of assets. It could be stocks, ETFs, and also mutual funds, bonds. And at this point, the portfolio typically is based on well-known mean variance model that you can find in the traditional corporate investment finance textbook. The Marco Sweet's mean variance model is the basics for a lot of this portfolio model currently used at this point in time. Okay. So this picture basically shows how it works. So the chart on the right-hand side is the classic mean variance model based on the risk preference of the customer, the return expectation, investment horizon. The system will try to come up with the red dot on the curve. So this is the optimal portfolio for this particular person with this particular risk profiles, return expectation, and investment horizon. And the basket of assets for the portfolio is predefined. So now. So this is the very traditional approach, but increasingly how this portfolio, optimal portfolio is constructed for a particular customer rely more and more on machine learning model. So here's one example to illustrate this. So again, the input the same thing. Risk aversion, returns, covariance of different asset and also the investment horizon, asset price and things like that. And then going through layers of neurons. So this is a deep neural network. And then the output. The output will be the weight of the asset in the portfolio for that particular person. So actually mapping input and output and a lot of research is going on in this area. The first example I'd like to mention is AML and suspicious transaction screening. I would like to maybe mention one project that we have done with a bank. Actually, very simple problem, but turns out to be very difficult to solve. So this is a typical transaction flow of a wire transfer. So a customer may walk in a bank and want to do a wire transfer to someone overseas. So they have to provide all the details, the recipient, the receiving bank's account, and all of these things. So before the transaction is executed, the bank will first do some kind of checking. And one of the checking is to check the name of both the recipient and also the sender, whether they are on the sanction list. Now, this action oftentimes trigger a lot of false alarms. Now let me explain this a little bit. So many financial institutions for AML and compliance purpose, they subscribe to information vendor. For example, WellCheck. So if a customer say John Lee, which is a very common name, want to do a transfer of $100 million from Hong Kong to Malaysia, say. And then the bank will first check, to another person like Mary. Then the bank will check whether John Lee and Mary are on the on a well-checked sanction list. The list consists of, I would say, maybe around millions of people. All this, including the PEP, terrorists, and people sanctioned by different countries. So if this name, for example, John Lee, appear in any of this list, there will be alert. And that's why it caused a lot of false alarm. Once there's alert, the bank will assign a human compliance officer to look into the case. So it's a very labor-intensive, especially when you have a lot of false alarm. Now, the false alarm comes because, in this case, John Lee may be the name of a building, John Lee Building. It could be John Street and Lee Building. It could be the name of a vessel. So it's not a name of a person. But somehow, if this name appear in, say, the free text of a street transaction, the alert will come out, causing the false alarm, and then waste a lot of people's effort to confirm it. So this is a little project that we have done with a bank. The problem is very simple to understand. So in the free text, which, for example, the remark field or the transaction detail field, which is a free text field of a street transaction. Can you identify the address in the free text? So the text may say, well, this wire transfer is used to settle this good to be shipped to this address. But somehow the name John Lee appear in this street address. So alarms pop up. So this is what we done for the bank. We use machine learning using natural language processing techniques to help the bank to try to find out the address, if that's one, in the free text. So if any alarms involving a name, which appear in this address, this is false alarm. So no need to ask the human subject to reconfirm it. So again, we are talking about machine learning here. The algorithm that we use is the naive Bayes classifier. So it's not a neural network. It's one machine learning algorithm. We need data, and the banks cannot give us any data, because the banks follow strictly the guideline of HKMA, so no data can be released. So that's create a challenge for us. So we have to be creative. So what we have done is actually we collect data, our student data, of course, taking out the names. We only need address. So we collect address from our local students and also international students. And then we form a training sample of almost 32,000 addresses. And then we apply this naive Bayes classifier to do the training. So the task is to pick up an address, if there's any, in a free text document. So it turns out to be quite good in terms of performance, based on testing sample. Again, don't test your model using the training sample. Test the model using some new set of data. So the accuracy that we have achieved is 97%. So not bad. And we actually share this with the bank. So this is one very simple example of how machine learning can be used in supporting daily operation of AML. So let me skip this. Okay, so this is we're running out of time. Maybe I just mentioned one ongoing research at HKUST. It's about fake news. So fake news is a big topic these days. A lot of people talk about fake news and how to fact check news. A lot of services have been provided to do fact checking of general news. But financial news is a little bit different. You don't have a lot of confirmed fake financial news. If you want to get some news about a firm, about a country, about an industry, well, you go to the reputable data source, for example, Bloomberg and Reuters. And these are trustworthy sources of financial news and data. So, for example, Reuters News Analytics, this is actually a service. So it provides you score in terms of the relevance and also the sentiments of any news about a particular company. It updates in real time. So it's already becomes a services. So if you want to know about the sentiment about a firm at any point in time, you go to one of these services, you get a score, positive, negative, neutral, and also now relevancy. So what we are interested is not sentiment, it's about fake or deceptive. So here's the two articles. General news. One is trustworthy from New York Times, and the other from a well-known fake news source, The Onion. So if you look at the title, no need to look at the extract. So the fake news for the title here is North Korean celebrates Kim Jong-un becomes first man to walk on moon. I mean, you just look at the title immediately. So even fact checking, you know this is fake. So for political news and general news, I mean you can spot it right away, or you can do fact checking. No, but for financial news, first of all, you don't have a lot of confirmed fake financial news. Many of the news, they are actually from reputable sources. So the question that we have is, it's not about fake news, it's about deceptive news, or in other words, whether a piece of articles or news about a firm, they are written in a way which is very similar to fake and deceptive news. So if you look at the bottom level, you see model deceptive score here. So this is the model that we developed using machine learning. We actually score how deceptive is this piece of news. Now we are not saying that this is fake. We just score and label it whether the way this article is written resemble a fake news or deceptive news. So in these two examples, it's shown that well, these two articles are from Bloomberg. I don't think they are fake news. But in terms of the way they are written, they are different. And that will cause an impression from the readers. Now, why we interested in this? Because if a reader, an investor, read a piece of information and they think that, well, they kind of are not very trustworthy, not the source, but the articles, they will not act on it. So we want to know the relationship between the amount of deceptive news about a firm and the trading volume on a particular day. So it requires both inferencing and prediction. Now the prediction part, we need to use some machine learning techniques to actually score every piece of news. And this is the So this is the architecture of the model. Actually involving something called a domain adaptive learning. We process millions of news to build this model, and we use this model to score hundreds of thousands of news about listed firms in the U.S. And then we try to aggregate the news for each particular firm on a particular day over a period of 5 years. and then we check the relationship between the trading volume, okay, as well as the extent, okay, a firm, okay, has, okay, this deceptive news, okay. So it's an ongoing research project, okay. Hopefully, okay, we will get some result, okay, in a couple of months. Okay, with that, okay, well, okay, it seems like I have achieved the impossible task, okay, to go through, okay, more than 100 slides, okay, in less than 2 hours, okay. I'd like to, okay, acknowledge, okay, some of the contents actually provided by my colleagues, okay, Professor Kai Long Hui, Professor Yang Yi, Alan Kwang, and others. So I stop here, okay, and then I think timing is right for the Q&A.
Thank you so much, Professor Tam. I think it's a very insightful sharing, and it sort of reminds me of my lecture time. But of course, there are not more to learn nowadays than the times that I study neural networks and stuff. I still remember when I did artificial intelligence at universities, neural network is one of the subjects that we all don't have a clue at that time, because I think you explained it very well. I didn't know that I were in the second winter of AI. Yes, and I think during that time, I think the only thing that work is expert systems, probably. And the real practical things that we can see as a household is our rice cooker. I still remember the fuzzy logic that was built into the rice cooker, and that was the only things that we can understand or feel what AIs can do. But of course, nowadays, after all these explanations, we know that there are machine learnings, deep learnings based on neural network. And I realized that as a household, as a general person, you realize that AI is not only rice cooker nowadays. I still remember when I first bought my robot vacuum cleaner. It is a little bit stupid, and it bumped into things and didn't know how to get back to the home base. But now, after weeks of training, it's now walking so confidently, navigating my home. So it looks like, I believe there is unsupervised learning built into that vacuum cleaner, and it's more affordable now to get those devices. So we have received some questions, and I think I'll start with some simple ones and getting harder and harder. Hopefully we can give our audience more perspective. I think the first half hour, honestly, it's pretty easy to comprehend, and getting more difficult towards the end, as our audience can see. And when I look at the audience list, there are very senior people. So we will start with some questions that might be asked by senior bankers or financial practitioners. So first is a simple question. Based on all your sharing, is data the most essential stuff to make AI to work? If a bank don't process the data, we don't need to ask whether we need to implement any artificial intelligence model. Is that right? Or?
Yes, data is perhaps the most important. Okay, so I mentioned earlier on in one of this chart about AI winter. So the second AI winter end in 2006 with the introduction of deep learning algorithm. But deep learning is not enough. There's another project actually started by Professor Lee in Stanford. So that project is very influential. It's about data. So she has collected a lot of data and about the visuals of different objects. Millions of them, tens of millions of them, and they actually manually label this data. So that's create a large base of data to experiment with different learning algorithms. So data for sure is very important. And when we want to develop machine learning application, first of all, we have to ask ourselves, do we have enough data in-house? If not, is there any data that we can actually purchase from outside? And also looking into the future, when the bank or a financial institution want to develop new IT application. Put in mind that you may need this data in the future. So when you design a system, you have the provision that put in place, an infrastructure put in place that you will need the data. So that's very important.
Okay, so where can those data coming from? I mean, one of the examples that you share, the local restaurants, and some of the data are actually public information, right? Like weather reports, weather data, all that. I would still remember 10 years ago, I met a startup. They actually make use of weather and traffic data in the US to predict the retailers' earnings forecast. And they actually did a good job, and a lot of these retailers actually subscribe, and also the financial analysts subscribe to their services. So if I'm a bank or if I'm an insurance company, so besides the data set I have, what sort of other data set could be relevant to us?
Well, there are a lot of data, for example, social media data. You may not have this data, but if you have a partner that works with you, and of course, you need to get the consent of the customer. A non-financial institution partner working with you on other projects. Then you may work with your partner and try to get some of this data. For example, a loyalty program between the bank and the retailer. So you may want to gather all this non-financial data from different sources. And there's a new research direction going on. It's called federal learning. So federal learning aims to address the data piracy issues. So you collect data from different sources, and then you try to group them without revealing the identity or the personal credential of the subject. But at the same time, you want to learn as a whole the pattern, the similarity of this group of subjects.
So federated learning is also one of the areas that we're looking into, because for one bank, it might only has a limited amount of data, but collectively, if previously a problem can be resolved, we think we can actually help the banking systems to enhance risk management. One of the examples that you've shown is actually suspicious transaction reporting. How can we make it more efficient in handling the false positives and that kind of thing. So one of the subjects that you talk about is overfitting just now. And is overfitting good or bad, or it depends?
Well, if you want to memorize things, not to learn, if you want to memorize some things, overfitting is good. But you want to learn, learning means that you try to generalize it so that you know how to act on or make decision when you come across a situation that you have never experienced before. So this is learning. So overfitting is no good for learning. So you have to strike a balance. A complex model can help you to actually fit all the data in your training set, but it may not be general enough for new events. If you want to just memorize things, then overfitting is good. Because it's not learning; it's just memorizing.
All right. So let's get to some of the questions from the audience. This particular question is more on the insurance business. The audience asks whether you have involved in projects using artificial intelligence on insurance-related business.
Well, we work on something at the tools level, but I mean, insurance is a big industry involving a lot of things. For example, some of these things involving natural language processing can be done also using some of the standard techniques for fintech in general.
Mm-hmm. And I think in insurance industry, they base a lot on, they also do a lot of modeling nowadays, right? But those are more traditional statistical models, I believe, right? Maybe we'll hope to see there are more usage of artificial intelligence. Actually, some insurance products out there is based on data that you got it from your wearables, like the IoT, and those are also useful.
The health status, I would
reduce
suggest
your premium.
Yes.
Yeah.
So I think experimentation is very important. So there's so many data that you can collect, and there's so many different algorithms. So I think the organization should have a experimentation kind of a mindset. Try new things and then learn from it.
Right. But I think if, even from one of your sharing, very senior officials as audience today can learn a few things about the how they can actually question their colleagues, right? And for example, you talked a little bit about the model validation. So I guess they can use those to question not only their own colleagues when they are proposing new AI models. They can also, if they are the CTO of the companies, they can actually also question the vendors, how they validate their models. But one question is, with the examples that you shared on retail, the restaurants, so advertisement could be one factor that you identified as, for that particular case, not very useful to predict sales. So I think these kind of exercise can also be done by banks, right? Because they want to increase their sales, and they also can use different models to realize which particular models will work best for them. So have you actually, for that particular exercise, have you talked to also the financial industries to see if they are interested to apply those models?
Yeah, I think these are the model that I mentioned. The linear regression models actually cover in freshman statistics.
Right.
So Excel has a built-in function. So it's very easy to use. All you need is to have the Y and the X, and then you can easily use Excel to run regression models. I think the most important part is how to interpret the findings. So once you know how to interpret the findings, it's very useful. Even though it's a very simple linear function.
Right. Sometimes you do not need to use a very difficult models or AI models to achieve what you want to achieve.
Right.
Another question that audience want to ask is, have you come across any systematic studies that shows that predictions by AI models, say in share price performance, are better than professional fund managers? So it's actually a good question. Would AI models be better than, so it tells us whether we should invest in the fund or just based on the AI models results?
Well, I understand there are a lot of research going on, both in academia and also in the industry, to apply machine learning model, AI model, to beat the market, so to speak. And they do a lot of course, there are a lot of data, and they build very complex model, back testing with past data. But I would caution this, it's like you're searching for something to fit something. And you can always find it if you look back in time. So the million-dollar question is it useful to predict the future?
Mm-hmm. So another question is, some of the statistical models are known to be very good at predicting the histories because they are based on historical data. But now the world changed so rapidly. In the past we do not have quantitative easing, but now we have. So how about AI models? Would it be the same? It can predict the previous histories, but it do not have the predicting power for the future.
Okay, so as I mentioned, having one of the slides, the basic principle is machine learning AI models work if there's a pattern. And this pattern is kind of embedded in the training sample that you feed into the algorithm. Now, if things are really random, or things are not that's happening in the future haven't been incorporated into the data that you use to train the network, then probably you are not able to capture it, and as a result, you cannot realize the benefit. So so be very careful about this, because you can always find a portfolio that can beat the market using previous data. So be careful about this. And if you really want to go into that direction, as just like the restaurant, you use it, apply it for a period of time in the future, and see whether it actually works or not.
One question is on data securities or cybersecurities, and so in the increasing adoption of artificial intelligence, do you see the risk of data and cybersecurity?
Yeah, I think data is very important because many of these models rely on a large amount of data. So for a financial institution that using machine learning, I think data security is very important. Make sure that your data infrastructure have a lot of the security measures imposed on it. So, and also policy from the regulators, how data can be used within the premises of a bank or outside, and also the data privacy issue as well.
Yeah, there's a last question. What is the possibility for data to play the role of, well, let me rephrase it. In a unsecured lending scenario, can data be used to replace tangible capitals like collateral? So this is more like a questions like for Henry, because because Henry just showed that a lot of the unsecured lending is based on artificial intelligence. He actually told us that within WeBank, there are more than half of the employees are engineers. I think it's very different from a traditional bank. So banks, do you see that is a possibility that credit assessment can be done in a better way than traditional approach, that you can help those unsecured lending to be approved without collateral? Okay,
I think it's all about risk management. And as a discipline, risk management has always relied on quantitative techniques. In the past, statistics, maybe now more tools, options available available for analyzing data using neural network, deep learning machines, and things like that. But at the heart of it is basically risk management. So.
Thank you so much, Professor. I think today we have a great discussion. I know that it's supposed to be a 100-hour kind of a class, but you compress it successfully into 1.5 hours. And I think we cannot give you a round of applause, but the audience can feel it that it's a very useful sharing. And so in case they have questions, I think they can also approach you and HKUST to see whether there could be potential collaborations between the academia and the financial firms. So thank you, Professor, once again.
Thank you, Nelson. Thank you.